Page 74. Right. Page 74. Is that the door? Hey. Hey. Oh, dude. Okay, as I was saying, page 74. The second derivative. Hey, did you give your assignment to Sylvia?
To Sylvia or to you?
Oh, give it to me. It's supposed to be Sylvia. You got a cover sheet on it.
Yeah, I want to Sylvia to get shipped out.
Right, just leave it on the desk before you go, okay? Right, so, again, as I say, page 74. Second derivative. So this here we know is like the slope of the tangent. The second derivative really means what you might guess it means. It means the derivative twice on function. So literally differentiating twice. Maybe some people have seen this before, the second derivative, but I wonder, does anyone know what it represents, the second derivative? So the first derivative is the slope of the tangent. The second derivative? Yes, to do with min and max, so a bit more general maybe. Yes? You know, this was supposed to be given to Sylvia.
The printer was broken.
That's fine, just sit down. Did you give it to Sylvia?
Yeah.
Okay, fine.
And Tony is helping me on to print this now. He don't have me.
Okay, great. Sit down. That's fine. Okay. So you were saying min and max for second derivative, which is right, but maybe a little bit more general than this. So what the second derivative represents, you could call it like it tells us something about the shape of the curve. Yes, did you give it to Sylvia? Yes. There. Huh? What's wrong with that seat?
He will fight you behind it.
He doesn't like me?
No,
Oh,
no,
there,
yeah.
of course.
Yeah.
He's not invisible, yes. Okay. So the second derivative tells us something about the shape. So for example, let's have a look at this here. Y equals x squared plus x plus 1. First derivative, what's that?
2x.
2x plus 1. And the second derivative?
2.
2. Now if I look at this, y equals minus x squared plus x plus 1. First derivative, minus 2x plus 1. And second derivative, minus 2. And in fact, you knew already that the minus in the front makes the hill shape. But actually you can know from the second derivative as well. If the second derivative is a positive number, you get this type of shape. And if the second derivative is a negative number, you get this shape. Now this type of shape has a name. Does anybody know? It's called convex. And this one here? Concave. So why is that useful? Well, as you said earlier, knowing this can help you decide if the point is a minimum or a maximum, because if it's convex, it means your turning point is a minimum. And if it is concave, it means your turning point is a maximum. So, yes? You got it?
Yeah.
Okay. You got a cover sheet on it?
I'm praying for you.
Hey. So, if it is positive, that means it's convex, and that means the turning point is a minimum. And if the second derivative is negative, that means it's concave, which means the turning point is a maximum. Let's have a look at some examples. It'd be useful to write these 2 points down. Okay. Yeah. So let's have a look at some examples. So, just a small example to get started. Let's calculate the second derivative. So here's our first example. Let's get the second derivative of this. So the first derivative is 15x, and the second derivative is 15. Okay, so that's boring. Let's do something more realistic to the exam. So in this question, find the stationary point of, yes, let's make it stationary point or points of y equals 2x cubed minus 3x squared minus 36x plus 36. So this is a good example to do first, because there'll be how many turning points? 2 turning points. One should be max and one should be min for this shape. Okay. So before I do anything, I have to get the derivative. So let's get the derivative. 6x squared minus 6x minus 36 equals 0. So that's x squared minus x minus 6 equals 0. Yeah? Okay, does this have factors? It does minus 3 and 2. So x equals 3 or x equals minus 2. So I'll get my y's now. We have 2 times 3 cubed minus 3 times 3 squared minus 36 times 3. Question? No? 2 times 3 cubed minus 3 times 3 squared minus 36 times 3 minus 36. So that's minus 117. Oh, right. What did I type in wrong? Oh, plus 36. Thank you. Minus 45. I'm pretty sure it's minus 45. I have it typed in here. And then the next one is when x equals minus 2. So if I put in minus 2, let's see what I get. And I get y equals 80. Yeah? Now we don't know which one is the minimum and which one is the maximum. So the way we decide is with the second derivative. So the second derivative is the derivative here. That would be 12x minus 6. Let's take our first point and put it into the second derivative. You would get 36 minus 6, which is 30, which is bigger than 0. So that means the shape here will be this kind of shape, is convex shape. And then here, I'll use a different color. We'll put this point in. So that means its shape will be equal to 24 minus 6, which is, hang on, oh sorry, minus 2. So minus 24 minus 6, which equals minus 30, which is less than 0, so that is a concave shape. So that means that this one is a minimum point and this one is a maximum point. So if I was to very roughly draw it, no, minus 2, minus 45. So that'd be something like here. And then minus 280 would be up here. And then 3 minus 45 would be down here. This first one, oh, hang on, no, that's not. Minus 280 is up here, and that's a maximum, yes. So this one was the max. And then 3 minus 45 would be over here, and this one we said was a min. So when we draw the shape, it should be convex for this part, but here it should, yes, should be convex for, English not working today, should be concave for this part, that's this one here. If I call this B and A, you make it clearer, that's B, that's A. So it's concave for this part, and then convex for the next part. Or min for this one here, which is, where's the numbers gone? 3 and minus 45, and this one is the max, which is minus 2 and 80. But you know that this is the shape of the cubic anyways. It goes concave and then convex. Now sometimes students think, and I used to think it too in school, that you can just decide its max or min by looking at the y. So this y is 80, that's clearly bigger than minus 45. So you might simply decide, well, that makes this definitely the max, and that makes this one here the min. Okay. Now, that is not always true. So in fact, last time, remember the graph I showed you with the log in it? That graph had two maximums. So you had one point up high, and then another point up high, and you might have thought, this must be the max because it's bigger than this one, which is the min, but in fact they're both maximums here. So maybe to help our English a little bit, we usually put in the word local max and local min. Because if you look at the graph, this is a maximum, but it's only a maximum in its neighborhood. It's not the maximum globally, because of course this graph continues up to infinity. So this isn't the maximum, it can go higher. So we say often it is the local maximum. And likewise, this isn't the minimum, because if you look to the left, your graph can go down further. So again, this one here is only a local minimum, not a global minimum. But on some graphs, like the quadratic, this is a local minimum, but also it's a global minimum because there's no part of the graph under this point. Yeah. So just be a little bit careful with the words local and global. All of these are always local, but only sometimes global. So for example, the quadratic is an example when it's local and also it's global. Whereas the cubic, it's usually just local, because the tails go up and down. Yeah?
These are maximum or minimum stationary points.
They're still maximum and minimum, but you can call them local maximums and local minimums. Because some people might think, like in this graph here, we shouldn't call this the maximum because there's many more points higher than it.
But these are not stationary points.
That's true, so you could also say the maximum stationary point, but most people just call that the local maximum. Yeah. But you're right, they're not stationary points. Yeah. Okay. Let's do another example, but I want you to try it. Can I go down? Yeah. So I'll give you an easy one to start. So what I want you to do is find the stationary point, and then by using the second derivative, tell me if it's maximum or minimum. Now you probably already know the answer because you can imagine the shape here. So what do you think the answer should be, max or min?
Max.
Max. But I want you to check this by using the second derivative. What's that? Oh, turn it. I've never seen that before. Okay, so let's have a look. The first derivative is minus 2x minus 14. You want this to equal 0, so then here we get x equals minus 7. We can put that back in to get the y. So let's see what we get. So minus 49 plus 14 times 7 minus 4. So I got 45. Yeah? Okay. So we have our point minus 745. The second derivative is minus 2, which is negative, which makes it a maximum, or if you want, a concave shape. So the graph looks like this, and this is a maximum at minus 745. Actually, I can draw that a little bit better. Minus 745. Because I actually know what this point is easily enough. What's this point here?
Minus 4.
Minus 4, yeah. So you can see very quickly I have a pretty rough but pretty good graph, like pretty quickly. Okay. Can we go down? Yeah. So we've done a quadratic, we've done a cubic. Let's have one with a log in it. So let's have a look here. Y equals log x6 plus x squared plus 8x plus 8. Can I go down? Now, first thing, before we differentiate, I should bring that 6 down. Okay, let's differentiate. 6 over x plus 2x plus 8 equals 0. Multiply by x. 6 plus 2x squared plus 8x equals 0. Divide by 2. X squared plus 4x plus 3 equals 0. I get two answers here. X plus 3, x plus 1. So that means x equals minus 1 or x equals minus 3. So I can get my y's as well. Let's see what I get. Log power 6 of, well, that's going to be 0 when I put the 1 in, plus x squared plus 8x plus 8. So this one here is just a 1. And then when I put in minus 3, I get a minus 0.408. So we need to decide which is max, which is min. So now I need the second derivative. Now before I write down the second derivative, let me write the first derivative again. But I'm going to write this 6 over x instead as 6x minus 1 plus 2x plus 8. Okay, now let's get the second derivative. That would be minus 6x minus 2 plus 2. So that is 2 minus 6 over x squared. So let's put in the first point. This goes in. And we get the second derivative is equal to minus 4, yeah. And then let's put in this point.
It will be 100.
It'd be negative as well, wouldn't it? 2 minus 6 over that number squared. Yeah, in the second one, you get minus 34. So because they're both negative, it means this is a maximum, and this is a maximum. So when you draw the graph, there's the first point here. Oh, well actually, and then in blue, let me keep the colours the same. There's the first point, and then, oh, I can make this neater. Problem? Yeah, what's wrong?
X minus x equals minus 3.
Oh, minus 3. Oh yeah, I put in the y.
Yeah.
Ah.
Oh, it's minus
2 minus 6 over 9. Ah, so it's not negative. It's positive. That's okay. So I guess this graph is not two maximums. So this is 4 over 3?
Yeah.
So positive makes a minimum. Alright, let's try and roughly graph this. So the first point I'll put in red, minus 1 and 1, so that'd be something like here. And then the second point is in blue, minus 3 and then minus 0.4, so that would be here. This red point is a maximum, so it needs to be a kind of hill shape. Problem? And then this blue point is a minimum, so it needs to be this kind of shape. So I guess my graph kind of looks like this. Yeah, if a question, please ask. I do make mistakes. Something wrong? Yes, thank you. My graph is so bad, it's not even on the right axis. So here, and then it should be down here. Still a minimum, and then here is still a maximum. Do you remember what happens to this graph at 0?
It gets closer to 0.
Yeah, it shoots down to infinity here, doesn't it? And then it comes back up as well. So I think it's going to shoot away like this, and then here it's going to shoot away like this. So I think if I graph this, I'll get some shape that looks like a cubic that fires down to infinity, and then something that maybe looks like a log that fires back up. You don't have to draw this graph in the exam. It's definitely not on the exam. It's just linear, quadratics, cubics, sine, cos, and tan that's on the exam. But I think it'll be good if we see what type of shape we get. Can I go down? Yeah. Okay, so in a second after I draw the graph, we'll just do this. Where is this one here? Concave. Okay. So just while I'm waiting to make the graph, this graph here will be cubic, right? So it'll have some kind of shape like this. So I want to know, where will it be concave? So on my picture here, where is this graph concave? Well, on the left, isn't it? So here is concave, 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 but not anymore. Then it switches to being a convex graph. So in this one here, I want to know, where is it concave? Where is the graph this shape? Now just before I do that, let's just quickly graph the last one.
How did you know 0 is one of them?
I don't. This is just quick sketch. In fact, I know that 0, if I look at this, I know 0 is definitely not a root because of the minus 9 here. Log x power 6 plus x squared plus 8x plus 8 Right, let's see what we get. Yeah. Which is what I drew. I said it's kind of a cubic shape on the left. It shoots down to infinity and then shoots back up. And then on the left, I thought it shoots up as well. So if you compare that with what I estimated, it's a pretty good comparison. Except in the it looks like the graph grows much quicker than I thought. So in my graph here, I had it going like this. But in fact, it looks like it grew much quicker than I was guessing. You see, it's very steep here. At 0.5, it's already up at 4. Okay, so if I kind of zoom out more, see how steep it is here? It's really growing very quickly. At 2, it's like at 20. So it's very steep graph. Okay, let me close that. Right, so any ideas on this one? How I could find the answer here? What I could do? Well, how do you know if something is concave? How do you know if it's concave shape? The second derivative should be, for concave shape, should be negative. So let's get the second derivative. First derivative is 9x squared plus 18x plus 7. And the second derivative is 18x plus 18. And if you want this shape to be concave, you need it to be negative, which means you need x to be less than minus 1. So what I'm saying here is, on the graph, when x is less than minus 1, it's going to be a concave shape. But then, if x is bigger than minus 1, it becomes a convex shape.
How do you know it's minus 1?
Here. Oh, this? Oh, I just brought the 18 over and then divided by 18. Yeah. So if I draw this, I'm thinking the shape changes at minus 1. Or it could be a bit higher. It could be more like this. It could be, it goes up, and then here at minus 1 is when it turns around. I don't know. Let's have a look at the graph. Okay, so we have, what was it, 3x cubed minus 9x squared plus 9x squared plus 7x minus 9. Okay, so if I graph this, my graph should be under the axis, but that doesn't matter. Maybe try to exaggerate a bit. Right, so let me just go down a bit. Oh, these are minuses. Go up a bit. No, too much. There we go. So look here, it's concave, and then it stops being concave at minus 2. Now it starts becoming convex. So do you see here, it goes hill shape, hill shape, hill shape, hill shape, and then here at minus 2, it's no longer a hill, now you become a valley. So convex here. Previously it was concave. So at minus 2 is when it changes from being concave to convex. And, sorry, not minus 2, I keep, minus 1 here, sorry. Minus 1 is when it switches from being concave, and at minus 1 it switches to being convex. So this minus 1 here is a special point when it changes from being concave to convex, and it has a name. Does anybody know its name? This point here. When it switches from being one shape to the other shape. Does anyone know its name? It's called inflection point. Here. And if you want to find where the inflection point is, you need to solve this equation, which is not too surprising because when it's positive, it's when it's positive, it's concave. When it's negative, it's convex. So when it's 0, that's when it's switching between the two. So this is how you can find the inflection point. You want to solve this here. So all you would do is change this to an equals, and you get x equals minus 1. Okay, suppose, we'll do another one like this. Suppose I ask you, I want to know when is this function increasing. So you know the shape of the graph, it's a shape like this. So here it's increasing, and here it's decreasing. For example, if you had a cubic, it increases twice. Here it's increasing, here it's increasing, and here it's decreasing. So my question is, how can you find where it's increasing? What could you do? Yeah, turning point, but I want to try and do it using these. Well, if it's, yeah, what do you think?
The second derivative?
Not this, not this. Not second derivative. If you want to know when a graph is increasing, that means you want to know when the slope is positive, yeah. Because when it's decreasing, the slope is negative. So that means if you want to know when this is increasing, you want to know when this here is positive. So that means you want to know when this here, the derivative, is positive, which means you want this. What did I write for? Minus 2x plus 10 positive. That means 10 bigger than 2x. That means x is smaller than 5. So for me, I think when I'm at 5, before I'm at 5, I'm increasing. But then after 5, I must start to decrease then. So I'm increasing as long as x is less than 5. So if I have a look at the graph, what was the function? Minus x squared plus 10x plus 8. So it's in blue at the moment. So you can see in the blue one, it's increasing, but then as soon as it hits 5, it changes and starts to decrease then. So while x is less than 5, over here it's increasing. So while x is less than 5, it's increasing, then it's decreasing. You can do the same thing for cubics, and if you did it for cubics, you'd get 2 answers because cubics increase twice. They're increasing at the beginning, then they're decreasing, then they're increasing again. So you'll get 2 answers for cubics. Okay, so just to finish, what I want to do is at the bottom here, there's a little table, and I wanted you to draw the shape for the different situations. So I'm going to do that one for you. You can draw it in your book if you want. So let's make the 9 different shapes. Okay. So look at the first box. The second derivative is negative in the first box. So what does that tell you about the shape? Concave or convex? Second derivative is negative. Do you see what I'm doing here in the box? Do you see that? So second derivative is negative. Concave or convex? Yeah, it's going to be concave. What's the story with the first derivative in the first box? Do you see what's happening here in the box? I tell you in each box what I want you to draw. So in the first box, the second derivative is negative, and the first derivative is negative. If the first derivative is negative, what's happening to the graph? It's decreasing. So we have here decreasing and concave. So let's draw a graph that's decreasing and concave. So that would be this type of shape. It's concave and it's decreasing. And the reason I don't draw this part in is because that is increasing. Right, if we look at the next box, it's concave, but the first derivative is 0. What does that mean? In the next box. Is the first derivative? Yeah, it's flat. It's a stationary point. But it's convex, so that means we must be looking at this type of shape, and we must be at the top of it. So it's this type of shape. The next box is convex and increasing. So that would be this type of shape. Okay. It's still on the first row, they're all oh sorry, I said convex, I meant concave, yeah. Concave, concave, concave. Yeah. Now the next one, the second derivative equals 0. So what does the second derivative equal 0? What's that called? Inflection point. So that means it's switching from being concave to convex, or vice versa. Now the first derivative is negative, so that means it's
Convex to convex.
it's decreasing, yeah? So we have two choices. We can either go concave to convex, but that doesn't seem right because in the middle we're increasing, but we want it to be decreasing, so it should be the other way around. We should be going from concave, convex to concave. I drew the same thing. Concave to convex. Now we only want the part that's decreasing. So I have a little bit too much here, so I should just have this type of shape. So that is when it goes from concave to convex, and it's decreasing. So the one at the end here is the increasing, and it's the other way around, so it's concave to convex to concave. So that was there. Okay, on the last row, I'll skip this one for a moment. On the last row we have second derivative is positive. So that is convex and it's decreasing, so that's this shape. At the end here it is convex and increasing, so that's this shape here. At the bottom here it's stationary point convex, so it's like this. In this box in the middle is when the first derivative equals 0 and the second derivative equals 0. Does anyone know what shape this makes?
Horizontal.
Not horizontal? In fact, you don't know. So when the first and second derivative, when they're both 0, we can't know what the shape is. It's possible it could be any of these 9 shapes still. If the first and second derivative are both 0, it could still be any of these shapes. Now I'll give you a very simple example of that. If I have x4, the first derivative is 4x cubed, and the second derivative is 12x squared. if I make x equal to 0, what's the first derivative here? It will be 0, and the second derivative will be 0. And the shape will be, x4 shape is like this. If I just change this to minus x4, this will be minus and this will be minus, but they're still going to be equal to 0, right? But its shape will be completely different. Instead of being convex, it will be concave. So my point is, when the first and second derivative is 0, you can't know what the shape is. And in fact, in some situations, it's not even convex or concave. It's this weird shape which we call a saddle point, where it goes like this. And this will be an example like x cubed. Now this part is not really so much on the exam, and it's not even on the syllabus, saddle points. Inflection points are on the syllabus, but saddle points aren't. So for us, we don't have to worry too much about this. If they're both 0, it means we don't know the shape. So then you might say, how can I draw it then if I don't know the shape? Well, then the only way to draw it is by making a table. This is the only way. Okay. You can write these in your book, I think, or in your notebook. I think it'll be useful here. Okay. Right. Let me tell you which ones to try. So in number 2. In number 2, WXY. Got that?
Yes.
In number 3, A, B, C. And do I have any increase? Oh, I don't have any cubics in here. I'll have to fix that next time. Okay, no cubics there. But I want you to do a cubic. Can you just write? Hang on here. Can you add this question at the end of number 3? And my question is, when is this function increasing? That's what I want to know. When is this increasing? Got this? Yeah? Okay. Now,